In our first two videos, we did something that felt like a little bit like hacking. We connected our ESP32 to the OBD2 port and we saw everything. A continuous, unfiltered stream of hexadecimal data passing through the car's network. It was incredible. Raw power. I replied to all the comments. The comment section was loud and clear. Most of you said, I need to understand this deeper. You want to know not just how to see the data, but what it is, how it's structured, and why this incredible communication system, the CAN bus, exists in every single modern vehicle. And honestly, to do anything advanced with the car hacking, you must know the language. The messages we saw has a precise logic. You can't manipulate the system if you don't understand the rules. While others just scratch the surface, we are dissecting the actual signal. If you want the power to reprogram your car's brain, watch closely. This is the real engineering. Think of engine control unit as a high-speed switchboard. It doesn't think. It executes a loop based on voltage and tables. ECU is a voltage monitor. It constantly reads electrical signals from your sensors, like the frequency pulse from the crankshaft sensor or the resistance change from the coolant temperature sensor. It's not feeling the engine, it's gathering the raw numbers to build a real-time digital picture of what's happening under the hood. And then the logic stage. This is where the engine control unit looks up the recipe. It takes your live inputs and compares them to the preset lookup tables stored in its memory. It doesn't just think or guess, it simply finds the exact cell in a 3D data map that matches your current RPM and load to determine the perfect fuel and spark timing. And then the action stage. This is the physical work. Once the engine control unit has the timing from the map, it acts as a high-speed switch. It completes the ground circuit for your fuel injectors and ignition coils, and by switching these grounds on and off at a microsecond speeds, the engine control unit physically controls the combustion that keeps the crank spinning. Mechanical timing and localized sensor data are only half the story. A modern car isn't a single machine, it's a distributed system. The engine control unit we just looked at is just a one node. If that node can't share data with transmission, the brakes, or the steering, the vehicle cannot function as a cohesive unit. That is the logic behind the last three videos. We weren't sniffing hex codes for the sake of it, we were accessing the car's backbone. Everything we have done, building the ESP32 sniffer and tapping the OBD2 port, was to reach the controller area network, the CAN bus. This is the protocol that governs how every component in the car negotiates for priority. In our previous lecture, we looked at the raw CAN traffic and played a game of probability. We saw the fluctuating hex values and made educated guesses, predicting that a specific ID might correlate to the gas pedal or steering angle based on visual patterns. Predicting and identifying the CAN bus messages that way is actually a pretty reliable way, but it's time-consuming, so we will use previously generated DBC files from other CAN bus hackers. Also, SavvyCAN has this function built in. We are going to use database CAN file, DBC files, the decoder ring for your car. This file takes the raw electrical noise and turns it into human-readable numbers like speed, RPM, or steering angle degree. Grab the CSV files in the video description. These are raw recordings from my 2014 Toyota Prius. We are pulling the DBC from the OpenDBC repository on GitHub. This is where the heavy lifting has already been done by the global car community. In order to download the SavvyCAN, you just need to go to SavvyCAN.com, scroll down and select your operating system, whether it's a Windows, Linux, or Mac OS. SavvyCAN is completely free and open source, so you don't need to pay anyone anything. After downloading, there's no installation process, so you just need to execute the SavvyCAN from terminal. After opening the SavvyCAN, go to the file menu at the top and hit Load Log File. Select the CSV file you have downloaded from the description. And once it loads, look at the packet count. We have over 80,000 frames captured here. Now, look at the file size on your disk. It's only 3 megabytes. Now, this is the ultimate proof of how efficient the CAN bus is. The car is transmitting a massive amount of data every millisecond, yet it barely takes up any space because there is zero waste in the protocol. Right now, look at the frame filtering list. It's just a wall of hexadecimal IDs. You see 0x245, 0x1c4, and dozens of packets, but you have no idea what they are saying. It's just noise. To fix this, we are going into the DBC File Manager. This is where we import the decoder ring, the DBC file for our specific car. Once we add that file, SavvyCAN stops showing you mystery hex codes and starts showing you the car's actual thoughts: RPM, throttle, brake pressure, and others. Go to your search engine and look for the OpenDBC GitHub. You will see a repository by AI. This is the exact database used for open source self-driving software, so it's as real as it gets. You can download or clone the whole repository if you want to run your own Python experiments with your car later, but for today we are sticking with the SavvyCAN because it is the most efficient tool for handling these files. Once you are in the repo, navigate to the DBC folder. This folder is a central library for vehicle communication. It contains the bit-by-bit definitions for almost every major car brand. Scroll down to the Toyota section and find the file named for the 2010 Prius. Download that raw file. The file is only 7 kilobytes. This is the tiny amount of data, but it is the mathematical blueprint for the entire powertrain. Think about the scale here. We have 80,000 hexadecimal packets that mean nothing to a human. This 7 kilobyte file contains the specific start bits, lengths, and multipliers needed to translate these packets. Without this file, you are just looking at a digital noise. Without this file, you're just looking at a digital noise. With it, you get the high precision data, RPM, exact vehicle speed, and gas pedal position down to the decimal point. We have got the log and we have got the map. Let's load it into the SavvyCAN and stop the guessing. Before we go further, you need to understand how a DBC file functions. It isn't an executable program, it's a plain text blueprint. It acts as a mathematical decoder ring that gives meaning to the raw hexadecimal frames we sniffed from the bus. Now let's look at the raw syntax on the line 83. Here we are, gas pedal, 581 gas pedal, and 8 and 3x. Now this line defines the container, the frame that holds the data. B0 underscore stands for the message object. It tells the tool that a new message definition is starting. This 581, this is the CAN ID in decimal. Let's actually translate 581 to hex. 0x245. Basically, it is, in SavvyCAN, this appears as 0x245. This is the unique address for the gas pedal data on a Prius. And this gas pedal here, this is a human readable name assigned to this ID. 8 here is a DLC, data length code. It tells us this message contains exactly 8 bytes of data. This 3x here, this represents the node. It indicates which engine control unit is sending the message. And we also have the signal definition. This specific instruction on how to extract a real value from those 8 bytes. This SG gas pedal defines the specific signal within the message. 23, and here, this is the location. This basically means start at bit 23 and count 8 bits. Basically, the 8 bits actually means 1 byte, right? So it tells us that tells the tool that it starts from the 3-bit and counts 8 bits. And here, this basically means the format. The 0 here means big endian. The plus here means the value is unsigned. which is basically positive numbers only. So obviously this makes sense because the gas pedal position cannot be negative, right? In this case, you can see here it's a minus for the steer torque sensor because the steer torque can be negative, for example, minus 30. That's why it uses signed numbers and not unsigned numbers. And this is the math. This is the most important. Now 0.005, 0. This is the math. This is the factor and offset. The first number here is multiplier. So we need to multiply that data that we are getting this from here, the 8 bits after 23rd bits. We are multiplying this to here. And the second number is the offset. So basically this data has no offset. And the physical value in this case would be equal to raw hexadecimal value that starts on the 23rd bit and ends after 8 bits, multiply by 0.005 and plus the offset. In this offset is 0. Now the range, this basically means the range. This is the basically physical value calculation, and here this means the range. This signal here expects a final value between 0, basically 0%, and 1. 1 here basically means 100% pedal press. And we also have the unit. It's a blank here, like percentage or voltage. And this here means it is in a receiving. Now, without this file, you see a hex value. Like, let's open the SavvyCAN. Yeah, without this file, you will see a hex value like 0x45, right? And you have to guess what that means. In previous video, we actually guessed it correctly. It wasn't hard, but of course, right now, it's very easy. Now, with this DBC file, the math is forced. We'll go to File, Load, right now we will go to File and press on a DBC File Manager, press on Load. We can also create a new DB here, but yeah, if you don't have the DBC for your specific car, you will be doing a very good work if you would create your own DBC for your specific car model and sharing it on the internet. It will be so good. Press the downloaded DBC file here and press on Save and press on Label Filters. And here we are. You can see here on the frame filtering, text here is appeared, and as you can see here, gas pedal is written here because the name was the gas pedal. And if we go to sniffer, let's actually clear the frames, go to send frames, playback, load file, and load our Toyota Prius, save the log here. Playback speed, let's make it 10 milliseconds per packet. And here we are. You can see here, the frames are loading like similar to real time. You can see there, the data is coming. Right now, I will be pressing, and here you are seeing the hexadecimal values and frame numbers. The greens you are seeing here basically means the data bit is increasing. The reds means that it's decreasing. And that wraps up today's lecture. You've seen how engine control unit processes data by mapping sensor voltage and resistance through internal tables. We have also deconstructed a real DBC file to show the exact math required to translate raw hexadecimal into physical values. No more guessing, just raw data. In the next lecture, we are moving to manipulation. I will be sending CAN frames to my Prius to override its systems. Like and subscribe so you don't miss the injection demo. Thank you for watching.